Another canonical problem that we'll see quite a lot in this class is the traveling salesperson problem. In older books, you'll see this referred to as the traveling salesman problem, but I really want to be an equal opportunity algorithmist here, so traveling salesperson problem it is. And I'll usually try to just abbreviate this TSP. So if you see TSP, that's what I'm talking about. So the traveling salesperson problem, or the TSP, works like this. You're given n cities. So think about just a city in the world or the country. So given n cities and all the distances between all the pairs of cities, right? So the specification of this thing is fairly large, quadratically large. So you're also given the distances between all the cities, right? If you like to think in terms of graph theory, you're given a complete graph on the cities where the edge of the graph determines the distance between the cities. And your goal is to find the shortest route that starts somewhere, visits all the cities exactly once, returns to its original starting location, and has a minimum total distance, right? So your goal is find a route visiting all cities returning to its initial location. So it's returning to its starting point. And return to start of minimum distance. Okay, so it's a simple problem, right? It's a simply stated problem. Now I've just said it. Now you understand it, right? You understand the problem. It turns out this is an extremely difficult problem to solve, and it's the topic of an amazing array of approximation algorithms. So there's many people who have studied how to solve this problem quickly, respecting this kind of surprising fact that we don't know a good algorithm for solving it exactly. So let me just give you a flavor of why this problem is hard to solve. And all I'm going to do is give you a flavor. I'm not going to prove anything to you right now. I'm just going to talk a little bit about what the challenges are intrinsic in this problem. So let's do one example right here. So I'm going to draw an instance of the problem. Call this example 1. And I'll say there's 3 cities, A, B, and C. And the distances between the cities are the following. The distance between these two is 4. Distance between these two is 1. Distance between these two is 3. Okay. And so the question is, how do we find the shortest tour of all these cities? Well, in this one, the question actually ends up being somewhat trivial. But let's just write these out and see what we can learn, right? So let's think about what an exhaustive search would do here. So an exhaustive search algorithm writes down all the possible answers and then just finds the one with the best objective value. In this case, it finds the one with the smallest cost. So we'll write down. Let me just warn you, this is a bad algorithm. If you see exhaustive search, that's typically a signal that you should raise your hand and say, hey, I bet I could come up with something better than that. So bad algorithm. But it's an algorithm that'll teach us how to think about it anyway. So write down all possible tours. To find the best. Right. So what are the possible tours? Well, we could go A, B, C. And that has a cost of 8, right? We could go A, C, B, has a cost of 8. We could go BAC. BAC has a cost of 8. The writing down the cost is going to get boring here, right? Because they're the same for every single one. And so BAC, or we could go BCA. We could go CAB, and we could go CBA. Okay, all with a cost of 8. Right, so how many are there, by the way? How many of these are there? Well, there's 3 factorial, right? So 3 factorial possible tours. How do I know that? Because I have memorized, right? This is a helpful thing. I have memorized that the number of permutations of an array of n elements is n factorial, right? So there's 3 factorial because this is all permutations of ABC, right? All reorderings of ABC is the number of permutations, okay? So let's notice something. First, several of these are the same, right? So ABC is exactly the same as BCA, right? Okay, the only difference is that one is rotated from the other, and that's also exactly the same as CAB, right? So if I look at my plot here and I go A, then C, or sorry, A, then B, then C, you know, that is this tour, and regardless of which of those 3 red circled things that I choose, that's the tour I'm taking. All I'm changing is the exact starting city. Okay, so those 3 are all the same. They are even if there were more nodes here, those would all be the same. And then ACB, BAC, and CBA are also all the same. Okay. The other thing we can notice is that you know, so those 3 are all the same. So that means we can throw out all but one of each of them, right? So I can just say, let's ignore that and ignore that. We'll ignore anything that doesn't start on A because it's the same as one that does start on A. And so I'll ignore that, and I'll ignore that. And so then in some sense, all I have left is these 2. Ooh, that does not work on the... all I have left is the top 2, right? So really, there's only 2 here. So really only 2. Only 2, which makes it feel like, hey, maybe we're gonna be in good shape, right? So maybe we're gonna be okay. So what are our observations here? Well, one is that the starting node doesn't matter. Doesn't matter, and so that takes us down to there's actually only n-1 permutation or n-1 factorial things, because as long as I pick a starting node arbitrarily and then, you know, find all permutations of everything else, that's really all the problem is doing. So I actually only have n-1 factorial things to check. And then 2, the direction of the tour doesn't matter, right? So, you know, I got it down here to 2, and then I can notice that, hey, those are just opposite directions of the same tour, right? So those 2 are actually identical as well, right? But these are also identical. Okay, so starting node doesn't matter, and then the direction doesn't matter. So really, we only have n-1 factorial over 2 possible solutions, right? But anything factorial is going to be nasty, okay? And so, you know, it's worth thinking a little bit about how fast this function grows. So let's just look and see for a problem that has n cities, how many different solutions are there? So for a TSP with n cities, how many unique solutions are there? Okay, well, it turns out a lot, right? So that there are, I mean, this is the expression, n-1 factorial divided by 2. And so we can actually work this out for some. So suppose n here is 3, well then, 1/2 n minus 1 factorial is only 1, like I've just shown above. Right? There's only one unique way to visit 3 things. You just pick one and walk around. But if n is 4, then this jumps up, and we have now 3. Say n is 5, well, then there's 12 possible tours, which is okay. We can live with that if we need to. If n is 6, then there's 60 possible tours. So this is growing fast. If n is 7, then there's 360. So that should make you worry, right? You jump from 12 to 60 to 360. That's reasonably fast growth. I mean, of course it is. It's factorially fast growth. So let me jump to 10. So 10, I have 181,000 tours with just 10 cities, right? There's 181,440 ways of visiting those cities. So 181 for 40. Suppose I jump up to 12, right? So 10 to 12, right? 10 to 12. All right. This is not a big jump. Now I have 2 times 10 to the 7th tours. All right. What if I have 20? If I have 20 cities, well then I have something with 16 zeros on it, right? So something like 6 times 10 to the 16th, right? Which is, I mean, that's a number that is it's a real number, but it's also a number that we'd rather not do any computation with, right? So this is a problem, right? Here we've got bad things happening here. So practically speaking, with the TSP, if you need to enumerate 360 different tours, you can handle that, right? You can write an algorithm to do that, but you can't practically hope that an algorithm is going to be able to enumerate 6 times 10 to the 16th tours, right? That's a problem. And so it turns out that the traveling salesperson problem, the TSP, is one of these problems that, partially due to the massive space of its solution, or its huge solution space, and partly due to the fact that it has some structure in it that makes it very difficult to solve. This is a problem that we cannot actually solve exactly if there's any large number of cities. And so we'll be using this problem to kind of prompt questions of how do you deal with that? What do you do when you can't solve a problem exactly?